So this is the question, which is actually what we have is a DC machine as similar rating as was discussed in example 4.2. It is connected to 100 volts DC supply and is operated as shunt motor. At no load condition, the motor runs at 1000 rpm and the armature takes 6 amperes. So the motor is not loaded. It is source is connected 100 volts DC supply source, and for our DC machine, a shunt motor, we know that V terminal, there is a current I terminal flowing, there is IA and we have IF, we have the field winding resistance RF, and we know that this RF is equals to field winding plus R adjustable, or it is also wrote as field control FC resistance. So, and at this condition, the armature takes 6 ampere. IA is equals to, we have 6 amperes current that is flowing into the current at no load. So the first requirement is we have to find out the value of the resistance of the shunt field controlled rheostat. So we know that EA equals to, for this machine, this is EA, it is a motor, so the sign changes, VT minus IARA, the direction of current is actually changed. So at terminal we have 100 volts, so we have to calculate how much voltage is induced, internally generated EMF, and IA it is given, it is 6 amperes, and RA is given to us, that is actually equals to 0.1 ohms. So RA equals to 0.1 ohms, and this will become 99.4 volts is EA, internally generated voltage, that is 99.4. And we have the magnetizing curve for the machine. So, and this is at 1000 rpm, machine is rotating at 1000 rpm. So 99.4 is actually this is actually 100 volts at 1. So 99.4 is little less than this, and it will be something here. So 99.4 will be here, and we can assume that this voltage is produced when the field current that is flowing is around 0.99 amperes. So why this is important is because we have to calculate when the current, the field current that is 0.99 ampere, it is flowing through this. So what will be the value of RF? RF is equals to VT over IF, and VT we know is 100 divided by 0.99, that is 101 ohms. And we know that RF is actually equals to field winding resistance plus R adjustable resistance, that equals to 101 ohms, and field winding resistance is 80 ohms. So this is actually 80 ohms. So what will be the value of R adjustable? That is known as field control. This is actually R adjustable, as same thing but with different connotations. So this will be equals to 21 ohms. So at the value of R adjustable at no load condition, when the machine is taking 6 amperes of current, is 21 ohms. Now the second part is related to find the rotational losses at 1000 rpm. Now this is our machine, no load is connected to this machine, and we have actually connected a battery of 100 volts, and the current that is being drawn by the armature IA is 6 amperes here, the IA. So, and it is no load connected to this machine. This means that all the power that is being drawn by the machine at this condition is actually the power that is being consumed for the core plus mechanical losses. And these losses are also known as rotational losses in the machine. So we can see that the no load machine rotational losses will be equals to EA IA, that is the armature current and the voltage induced in the machine, and that is equals to EA we have calculated 99.4, and IA is basically equals to 6 amperes. So P rotational for our this machine equals to 596.4 watts. So next part, the part C states that find the speed, torque, electromagnetic torque, that means the converter torque, and the efficiency of the motor, that is P out over P in, when rated current flows in the armature. So what is the rated current? Rated current for this machine for the armature was 120 amperes. And what it is now asking us to calculate is that we know that EA no load that we calculated previously was 99.4 volts. Now EA full load is actually equals to, let's see, VT minus IA RA. Now it is fully loaded. The machine is now loaded. What is meant by loaded? So if this is our motor and we have connected a load with the machine, rated load, it is rotating this load, and now the current IA has increased to 120 amperes. The voltage again here is VT is 100 volts. So after we have done this, what will happen to the internally induced voltage? VT is 100 volts minus IA, and IA is 120 amperes and RA again is 0.1, and so at the full load this voltage will become 88 volts. This will be 88 volts. So now the question is, what will be the speed of motor when it is fully loaded? It will not be equals to what it was initially, and it will of course decrease as internally generated voltage has also decreased. So this can be calculated, because let's look at this relationship. At full load, K flux full load, and we have omega full load, and if we find a ratio between no load divided by machine is the same, no load omega no load. Now machine constants are same at full load and no load. The terminal voltage, we can see this field current is dependent on terminal voltage. It is fixed 100 volts, so it will not change. So both the fluxes are also the same, they will cancel out. So at full load we can calculate the speed at full load will actually be equals to EA full load divided by EA no load into speed at no load. Now what is the speed at no load? We know it is 1000, and actually what will happen in this case is we will first, because this is omega, so what we can do, we have to convert in radians per second, and then we have to convert in this. But if we modify this formula, for example, this formula was representing speed as in RPM. So we can say that this is why what I am trying to do is, so I don't have to convert to radians and then again to RPM. So if we here at full load, this was 1000 RPM. It's given in the question. At full load, it is 88 volts. At no load, it is 99.4 volts. So the speed at full load would be 885.31 RPM. This will be the voltage that will be, this will be the speed when the machine is loaded. So now to convert this into radians at full load, we can multiply to 2 pi divided by 60. So in radians per second, this would become 92.7 radians per second. This is the angular velocity in radians per second. That's the speed in radians per second. Now, that was the first part, that we have calculated the speed. Now let's look at electromagnetic torque. So to calculate the electromagnetic torque, as we have seen in the power diagram also, it is actually the power converted. And the power converted in the machine is EA, IA is converted into torque applied into speed, mechanical. So this is actually when it is, so the induced torque or the electromagnetic torque that it is talking about is actually equals to EA, IA over omega m. Here it is radians per second, so we have to be careful. So the speed, the internally generated voltage that is for the machine when it is loaded is 88 volts, right? It is 88 volts, and the armature current at that time is 120 amperes, and the speed that we have calculated is 92.7. So we can say that the torque applied is equals to 113.9 Newton meters. This will be the electromagnetic torque. So in this part they have asked, we have calculated the electromagnetic torque and now the efficiency of the machine. So to calculate the efficiency of the machine, let's look at this. Now efficiency, for the efficiency we know that efficiency equals to P out over P in. Now P out is actually the voltage that was induced in the rotor, which was later on converted to mechanical power, minus P rotational losses. If we can subtract these losses, we can calculate P output. And for the input power, so the input power is here. What will be the input power that is being input is actually equals to now remember, this is IA. IA is the current that is induced in the armature. It is not the terminal current. It should be, from this diagram we should know that IA, that is 120 amperes, is this current. It is not the terminal current. So the power that is input, P in, that is input, is actually VT into IT, and where IT is equals to IA plus IF. This should be clear to the students. And what is IF? IF we have calculated was 0.9. So it is actually equals to VT into IT. So VT into IT, that was the input power to the motor. So let's calculate first, let's calculate P naught. P naught is EA IA minus P rotational. So that was EA was 88 volts, or actually we have 88 volts into 120 minus rotational losses. We have calculated rotational losses are nothing less than the no load power being drawn by the motor. It was 596.4. So output power for our machine will be, if you calculate this will become 9963.6 watts. And now P input is VT IT equals to VT IA plus IF. IA 120, IF 0.99, and VT is 100. So this will become P in equals to is 12,099 watts. So therefore our efficiency will then become 99 and 9963. We have P output, P in, and so efficiency will be 82.35%. Now in the part, the last part, what it is saying is that for the given machine, so we are not considering the armature reaction. So in the part D, it is saying find the starting torque if the starting armature current is limited to 150 of its rated value. So this is another aspect, that when a motor starts, it is a loaded motor and it starts, so initially the motor will draw more current because its internal voltage, and that starting in the starting phase, the current drawn by the motor is limited in our question 150% of the rated armature current. So this means that the armature current in the starting of our machine is, that is 150% into 120 ampere. This is actually 150%. This means it is 1.5 times into 120A. That way the armature current for the machine will be 180 amperes. Now we want to know what is the starting torque at this condition when this current will be flowing. So torque is equals to K phi IA. So it will be 180 amperes. IA will be 180 amperes. Now how to know this? Okay, K is the machine constant and phi is the flux. So there is another way to calculate this. We know that the voltage at no load, and that is in the starting of the motor, we have this voltage that is equals to 99.4 volts, is actually equals to K phi omega m. When our machine is rotating at 1000 rpm, this is the flux. And so we have not changed the flux in our machine in any way, as we have solved all the example, because V terminal is fixed and only the speed changes with the time. So if we are able to calculate this expression and we can substitute this, so we can calculate the torque. So can we calculate this for the no load condition? We have this equation. Yes, we can, because omega, we can write omega here. So this is actually 99.4 is equals to K phi. This is the value we want, and this is required to be in radians per second. If we solve this, K phi equals to, actually the value that we will calculate from here will be equals to 0.949. And if we substitute this value in this equation, Ia we have 180, so we can calculate the starting torque of the machine. This is the starting torque, that will be equals to 170.82 Newton meters. I hope it helps. Thank you.